we have Nyrobi Whitfield.
Hi, my name is Nyrobi Whitfield. I am a senior undergrad at Oberlin College, and this past summer I was a Noah Holling Scholar at the Consistent Bay Laboratory with Dr. Paul Gico and Ross Whitfield. I'm excited to be sharing my project titled The Life and Tides of Trina Lake, where I will be defining the current state and future trajectory of a unique tidal lagoon system in Seldovia, Alaska. To give you some background, this past summer, I lived and worked for 9 weeks in South Central Alaska on the southern edge of the Kenai Peninsula and along the shores of Kashmik Bay, which is a subarctic body of water known for its extremely large tidal range of about 25 feet and super rich coastal ecosystems. However, this region has not always looked the way that it does now. In 1964, the Great Alaska Earthquake, with a magnitude of about 9.2, rocked the entire region, and the city of Seldovia saw its land sink by about 4 feet as a result. What's remarkable is that many of the residents don't report not even being able to feel the land sink beneath their feet, and it was only evident at the next high tide when their coastal region was suddenly inundated with salt water. One of the areas most transformed by this sudden change in elevation was the Trina Lake complex, which is a cluster of 3 coastal water bodies. But that's a really bad picture. So to give you a better idea of what it looks like, I created a context map using 2023 NOAA LIDAR data and GIS. And as you can see, the complex consists of 3 water bodies, which is Trina 1A, Trina 1B, and Trina 2. Ever since the earthquake, these once completely fresh water bodies are now brackish, and locals use this area for recreational purposes, and there are even reports that the main lake, Trina 1A, may serve as a haven and a nursery for ecologically and culturally important species such as Dungeness crabs, herring, and butter clams. But despite their unique ecological history and recreational value, the Trina Lake complex has remained almost completely unstudied until now. This takes us into the heart of my project, which aims to study the current state and future trajectory of this unique system. And to do this, I set 3 goals for myself. The first one was to create a standardized framework with which I could classify and characterize an estuarine system. The second goal was to then use that standardized framework to be able to characterize the Trina Lake complex. And then the third was to compare and contrast these water bodies to assess what drives their differences and to assess their ecological importance. So in order to accomplish my first goal of creating a standardized framework, I did a lot of research on different estuarine classification guides and combined all the pertinent information to create the table that you see here, with there being main components of analysis and modifiers to help me classify each of during the classification process and key questions to ask during the analysis process. So the main components that I studied were connectivity and elevation, bathymetry, water quality, and sedimentology, as well as biology. And due to time, I cannot go directly into what these all mean, but I think you all have background in ocean science. So that leads us to the methods section, where we used a wide variety of tools and equipment to analyze each of the components. For oceanography, we used moorings that stayed in the main lake, Trina 1A, for about 3 weeks. And we also used the YSI sonde to collect data at multiple points. For biological surveys, we did beach seines, clam digs, crab traps, as well as drop cameras. To assess sedimentology, we used sieve stacks to assess grain size distribution. And to collect bathymetry, we used a handheld depth sounder and collected hundreds of points from each of the water bodies. And then using QGIS and ArcMap, I was able to interpolate that data to create the bathymetry maps that you see here and we'll see throughout the rest of the presentation. So now that you have an understanding of what we assessed and how, we can move on to the fun part, which is using that information to classify each of the water bodies. For Trina 1A, we found that it has a direct connection to the ocean via a narrow tidal inlet. It is the deepest of the 3 water bodies with a maximum depth of about 3.86 meters and has near ocean levels of salinity at about 29.4 PSU. And for context, the ocean has about 31 to 32 PSU. The sediments here contain a mix of gravel and sands that were deposited from the ocean, and there is silt and clay in the deeper portions of the water body. Surprisingly, there was also some peat that we found on the perimeters of the water body, which is uncommon for systems that have marine influence. It was also by far the most biologically diverse of the 3 water bodies, supporting herring across all stages of life, as well as other numerous organisms. With this information, I was able to classify it as a choked because of that narrow tidal inlet, tidal lagoon. Trina 1B was much different than Trina 1A, to say the least. It receives its name as a result of an indirect connection to the ocean through Trina 1A via a narrow man-made culvert under a bridge. It is shallow with just about 10 centimeters of maximum depth, and is very warm as a result. Despite these limitations, it is still slightly brackish at about 5 PSU. And interestingly, again, this entire water body, we found peat in its depths, deposited under finer sediments. There was also very little biodiversity in this water body, and all of this information led me to the conclusion that it is a back barrier, meaning that it receives secondary tidal water, peat pond. And then finally, for Trina 2, we found that it has an indirect connection to the ocean via gravel berm that filters ocean water at certain tidal heights. It is also relatively shallow with a maximum depth of about 1.36 meters and has a very high, or a relatively high average salinity of about 26.5 PSU. Unlike the other two water bodies, its substrate had no peat and was mostly gravel and sand deposited from the ocean. This water body was also not very biodiverse, and this led us to the classification of a semi-enclosed due to that gravel berm tidal pond. So, what explains these differences in classifications? We found that the drivers appear to be connectivity, elevation, bathymetry, and sedimentology. It was noted that the water bodies with more direct connections to the ocean, such as Trina 1A, had a higher salinity and more diverse sediment layers. And this is likely as a result of the strong and frequent tidal exchange, which brings in and redistributes marine sediments while also increasing salinity. Bathymetry also seems to play an important role here, with deeper water bodies such as Trina 1A being able to retain marine water for much longer due to its higher volume capacity, while also helping it maintain higher salinities. Comparatively, shallower water bodies such as Trina 1B tended to lose its marine influence much more quickly due to dilution from its freshwater inputs that it also receives. So these classifications in the baseline work done in this project provides a baseline for modeling and predicting how the system will respond to the impending stressors like sea level rise and land rebound as a result of glacial isostatic rebound, as well as the land rebounding after the earthquake. So currently NOAA sea level trends show that Seldovia sea levels are actually dropping at about 1 centimeter per year. And at this rate of sea level drop, initial modeling suggests that the water body will lose connection with the ocean by the year 2115, once again becoming a freshwater body. So as you can see here, the Trina Lake Complex is an evolving system that will most likely continue to evolve over time. And that is why it is important to have a classification guide to assess these changes as they occur in the future. So with this in mind, in the coming months, I will be continuing my work for this project through my senior honors thesis, where I will be working to predict what this environment will look like in the future. The competing forces of sea level rise as well as land rebound will ultimately determine the fate of this ecosystem, and is my goal to figure out what it will look like in the future. And so with that cliffhanger, I will finish with my acknowledgements. Thank you to NOAA, of course, and the Holling Scholars Program for funding this research, as well as AGU and Oberlin for funding my travel to this amazing conference. And to Paul and Ross, my advisors, thank you for your support.
We have time for questions.
Hi, is the peatland pond, is it still producing peat, or is it the peat from before it was connected to the ocean?
My theories, I'm a scientist, but I'm not a PhD. We believe that it's from pre-existing conditions before the earthquakes, but it is all dead. But we were able to dig it out.
Thank you.
I have a great talk. Thank you so much. I have a question. So do you actually see tides go up and down in these lakes at all? Yes?
Yeah, we definitely do. We had a little camera that we posted out in front of each of the water bodies, and we were able to watch it. But you can see, especially in Trina 1A with the narrow tidal inlet, you can see the water slowly coming in.